there are some more questions which has to be done, and therefore that I will be doing at the end of this chapter. For example, there is a very good question on single linked list to how to detect a loop, and therefore, or how to remove a loop. There are a lot of questions, more than 10 of them are there. Therefore, we'll just be doing that. If you see from the last class, I had given you one of the questions which I expect that you should have done in the other way. That means the question where you have two linked lists which are having a common node, you can find other solutions for that, and at least you can find at least four solutions for that. That means there are at least four solutions which can be done in obviously not in the same time, but in different times. Now, therefore, shall I proceed with the other concept, or do you have to ask any questions on the single linked list? Okay, one thing, yeah, even okay. Now, one more thing which has to be is it? We call it a circular linked list. Now, circular linked list is a concept where the last node does not contain a null pointer. That means it is something like this. Okay, this is circular linked list where you will have the last pointer pointing to the first node, and that is similar to the circular cube. What we have done, therefore, there is no last, except that from where the start is going to begin, that is the starting node, and you can come back to the previous node. Now, in this means if I can simulate this, this could be simulated as a circular cube also. Therefore, what I can also draw like this. Okay, except that if I have one pointer over here, which is start, I might say there are four nodes. Now here, when you are going to find the condition that while say T of link is not equal to null, it will not be there because there will be no null over there. Now if I want to find the number of nodes, what I will be doing, I will make one pointer at the start, and then what I will be doing, I will be using that keep on incrementing T. Therefore, T will at the first node, then second node, then the third node, so on. When it is the last node, I will check the condition that T of link is not equal to start. Therefore, to find the to find the maybe the last node, it will be T of link is not equal to start. So here, what I mean to say by the last node means, if I am at the first node and this is the fourth node, there is the fourth node. There is no last over here, but just to compare with the thing, if this suppose I am going to use like this is the first node, this is the second node, this is the third node, this is the fourth node. Then in that case, fourth is the last node. So it is just like same over here, first node, second, third. Therefore, when I am going to do like this, it is at the fourth node there. Therefore, this is a circular linked list, which is where if I want to perform, say, insertion in a circular linked list, the same. If you want to perform deletion, the same. If I want to insert an element in a linked list, obviously, deletion insertion will be same, except that if you want to insert at the last, you have to insert here. You have to insert a node over here. Suppose I want to insert at the last, it will insert at the fifth position. And to do that, what you have to do is that you have to make like this, and then this has to be deleted. This is how you're going to insert a node. Okay, that means you go to the last, and then you have to insert an element at the last position. Now by this method, what we can do is that the insertion time will always be order of n. As we have seen in the single linked list, the insertion time will be an order of n. The deletion time will also be an order of n. Okay. Now, there is a question which has to be little tricky, but you have to find a solution for this. Now, the question is like this. Devise the method to insert a node at the end of a circular SLL in devise a method to insert a node at the end of a circular single linked list in constant time. That means what I drew on the board, the fifth node is the last node, and I want to insert the node at the fifth position, that is after fourth, in a constant time. A constant time already know it means that it should be independent of the number of nodes. Now, try to think over it, how it can be done. You know that insertion takes always an order of n times. Here also, but is it possible to modify in some way by which you can do this in this time, in the time of constant time? That means it must be done in the order of 1. It should be in order of 1. Now try to think over this, and let us come with a solution tomorrow. Try to find how it can be done. Is it possible to do like this? That can we find it in constant time? Okay, fine. I think you can do that. Any questions?
Sir, I have one question, sir. Sir, as we know that there are two loops, no? There are two loops. We can have the two loops, having the loop moving for n times. Then two loops having particularly order of n, of omega of n. Time complex. Then sir, then overall time complexity is omega of n. But overall time complexity we take omega of n. Why not sir 2 omega of n?
For what? See, for which question? See,
Yeah.
for this, see, if there are two loops which are nested, and
but not
both
nested.
of them is
Not nested, sir. They are independent.
correct. If they are independent, it will be over order of 2n only. See, suppose if I take like this, suppose I have a for loop. I have some statement over here. Again, I have another loop. Okay, these are two independent loops. This is order of n. This is order of n. Combined is order of 2n. Fine. What's the problem?
Sir, but actually the order of 2n algorithm exists. We used to take neglect the constants in time complexity.
Because if I am going to have this algorithm, then n is very, very large, 2n is also very, very large. It means that, strictly speaking, it is order of 2n. But why we do neglect the cost is because it is there that even if 2n is very, very large, even n is very large. Let us take example. If 2n is 1 million, n is also order of n is also half million. Therefore, in many of the algorithms, when I talk about order of n, it is not always order of n. For example, I take a equal to order of say n by 2. This is also order of n. For example, when I am performing selection sort may not always give an order of n square. It might be less than n square. But does not mean that order of 2n is equal to order of n. No, not at all. Order of 2n is bigger than order of n. But for some algorithm, we find that it is there. Therefore, if you go in the same, when you draw the particular the graph for this, for example, if you're going to find like this some growth, it's called a growth. In that case, you will be knowing that how it actually grows. Therefore, this is you will learn in the algorithm subject, that is called ADA, analysis and design of algorithm. In that case, you will know. But that is, we are not strictly speaking that it's order of n. Therefore, that you just brush up your knowledge, those not in this semester, that how to find the asymptotic notations. That is, you have to find for this. Find asymptotic notations, then you will know how the growth of the function is going to vary. Okay. Now in this case, what we are going to with this concept, suppose now I ask you that is it possible for you to simulate a queue using a linked list? You can very easily do that, because whatever operations what you perform on a queue can also be done in a single linked list. For example, insert. You can insert using, you can have 2 pointers. One, for example, let us do, because I want to do, say if I do Q, using single linked list. You can do that. I'll just give a brief introduction how you can do. Suppose I want to insert the first element. It will be something like this. You will have, say, a rear, and you will have a front. Then I want to insert one more element. Obviously, I'll insert over here. I move front over here. Now you want to insert over here the particular something. I want to insert one more element. I will have this. I have here. And I will have one. Now I want to insert one more element. I will insert over here. This is shift from here to. Again, I want to insert one more element. Now, what is happening? You are inserting in order of one time only, because once you are just shifting the rears. Now you keep on adding over here. You will be having, maybe you will have this here. So this is the insert operation. Now deletion. Deletion will be a little tricky, because you want to delete the element over here, you have to delete this element. For example, this is the element. Suppose I want to write like this. Suppose this is 1, this is 2, this is 3, this is 3, and this is 4. Now if you delete 1, you have to come to 2. But to come to 2, you have to again perform the traversal. So what will happen is that it cannot be done in order of one time. You have to start from, say you start something from here, I will have to start something from there. say I will start say with T over here, start moving T from here, T will come to this place, then I can delete F. I can delete 1. Now in the second case, again I want to delete, again you start T from here, move T to this, you stop T at this place, and then you can delete 2. And this will take order of n times. If a deletion will take order of n times, insertion will always take order of 1 time. Therefore, in this case, what will happen? Insertion will be done in order of 1 time. Deletion will be done in order of n times. But it could be improved. That is it possible for us to improve in such a way that I can do this? Now, I think this is clear to you. Insertion is nothing but insert at beginning. Now here you are going to call the algorithm insert at beginning. This is nothing but delete at end. And you know that delete at end takes order of n times and insert at beginning takes order of 1 time. Therefore, this is the normal thing. Now your task is that to improve this algorithm. Is it possible for us to improve in such a way that I can reduce the order of n? What shall I do so that I can try to reduce order of n times? Now think over it. Therefore, there are 2 questions if you think. One, the last one I gave you. And second, how to reduce this time? How to reduce this time? How to reduce this time? Order of 1 is always constant time. You can't improve upon that. But is it possible to reduce order of n so that deletion at n might take less than order of n? And if you could do that, obviously you are trying to do a much better approach. Similarly, you can also do for a stack. A stack using linked list. Okay, that also you can do. So let us try to simulate like this. Okay, but tomorrow let us try to find a solution for this. And is it possible to do it for this? Now, let's start with the double linked list. Now, this is more important a concept because all the problems of trees will be done using a double linked list. Therefore, practically this finds more importance in computer science than single linked list because there are 2 links over there. Now, in that case, it will be something like this. You will have a left, you can say left PTR, and you can say you will have right PTR. So this is the data part. Let's say the left pointer or the right pointer. Therefore, it is 2 pointers are there. One which is pointing to a node before this, and one pointing to a node after this. It means that you will have a linked list like this. Something like this, where the left part of a start will point to null and the right part of the last node will point to null. Now this is a double linked list. Obviously, this suppose some address is here. Let us take some addresses over here. Maybe suppose this is say 2120. This is say 2060. Suppose this is 2190. Suppose this is 24. Now this address is saved over here. This address is saved over here. This address is saved over here, and this address is saved over here. Therefore, that contains two link parts. Like you can go either left side or right side. Obviously, this is easier to maintain because even if you delete one of the links, you can very well try to go back. Therefore, that is little easier for us. But in that case, any problem which you are going to implement using a double linked list, the chances of getting it disconnected is little less, because the fact that you can very well come back even if you do that. If one of the pointers are lost also, you can always try to take the from the previous one and go there. If you can traverse from first to last or from last to first, both ways you can do. Therefore, actually, the problem is same as the before, except that if you want to create a double linked list, you have to first of all do the same thing, bring one node from the avail, and let us call it say temp. Then you are going to put the null at the left, null at the right, put some data, and that becomes the first node. Similarly, for the second node, you bring one node from avail. Either you can insert at start or end. Keep on doing. If all the algorithm what we have done in the single linked list, we have to repeat over here. Therefore, in that case, what are the algorithm we will need to do? We will need to do the algorithms. First of all, create a double linked list. Then insert a node. All the types A, B, C, then delete a node in double linked list. Again, A type, B type, and C. Where A is the thing, insert at beginning, B is insert anywhere, and C is insert at end. That means insert at beginning, any position, and at end. Similarly, the same one at beginning, then at any position, and at end. Okay. Therefore, these are all the concept of this one, and therefore these are the ways how you can do that. Okay. Therefore, this is the way how you can. Now, the problem is simple. I can do any one of them, and you can do the others. Then what I will do? I will try to do one of them in the insert. Now, create you already know. For creation, you can very well write like this. For create, what you will do? Bring one node from avail. And call it say temp. In the second part, you say temp of left. Is equal to null. You say temp of right. And you can put subtemp of data. That's all. And now you want to rename it. You can say start is equal to 10. Now at this, what you will get? You will get this. You will get like this. some data, what you can think, some data may be. After this one, you will get like something like this. Okay. By this method, you can very well do this. Correct? Now this is how you can perform. Now this is the same one, except that I have just added one more right pointer. Otherwise, if you see the previous algorithm, it just contained 10 left link. Here there are two nodes, left and right. Now in that case, what I have done, the node is having a left pointer and a right pointer. Therefore, either you can use LPTR, RPTR, you can use left right also. Okay. Now if from here, what I can do, I can now let us try to write an algorithm to insert in the middle. Now let us understand that the linked list already exists. Okay. Suppose the data might be, suppose let us take the data, we say A, B, maybe C, maybe R, maybe P. And I want to insert, say, some data B after C. Let us, question is, insert a D after C, or insert D at fourth position. Insert D at fourth position. Now this is the same question, except that what you have done previously just has to be changed. Now I will not write the complete algorithm, I will just write how to insert that. That means you have to bring one node from avail, let us call it new. Now what I will be doing, let us take like this, and I will be trying to insert the element over here. If I bring one new node over here, and I will call it new. I got one node from avail and I call it new. Now I should traverse. Now in that case, how you will traverse? It's simple. You just compare the data part of this. That means you will compare the data part of this. Then I'll just write the algorithm like this. Okay, I will write traversal. While T of data is not equal to say, so I want to insert after C is not equal to say C. T is equal to T of 9. Okay. Now in that case, you will have one T over here, you will have one T over here. Now T is not equal to C is correct. So T will move to B, then T will come here, and T will stop at this point. That means T will move 2 times from A to B, and here T will stop because here data is not equal to C, will become false, and therefore it will come out. Now you have already brought that new node. Now you have to add. Now how many steps you have to follow? Obviously, now you tell me how many steps you have to follow. How many things you have to do over here? Obviously, One thing is that you have to modify this. Second, you have to modify this. Third, you have to change the data. Fourth, you have to modify this. And fifth, you have to modify this. That means the left part of new, the right part of new, and the data part. Then the right part of T and the left part of the node which is not having any name, but that is the node after T. That means you have to modify the left of C, sorry, right of C and the left of R. Now the node C is having a name T, but R is not having any name. Therefore, I have only two nodes having name, one a new node and second the C. Now I'll just write those steps. Okay. Let me write the first step. बताओ. What I will do is that I have to connect that new. I have to do is that what I will do, I will have to put over here like this. Like this. I have to put the address of T into left of new. What should I write? Okay.
So new left is equal to T हो जाएगा.
New of left. Now, in that case, what you can do is that here you can also attach like this. Second. Now the name of this is T of right. And new of you have to put the address of R. But address of R, you do have no name. But this address of R is saved in the right part of C. It's saved in the right part of C. Therefore, what I can say T of right. Fine? T of right is nothing but the address of R. Then what is happening is that this address, suppose, just take this address, suppose 2400. This is already saved over here. It's already saved over here. Therefore, what I can do, if I write 2400 address of R, it is same as right of C. Therefore, it is T of right. And therefore, this link is now established. Now, what you have to do is that the third part you can directly put. Not a problem. Your data is equal to anything element. The fourth one is that you have to modify the right part of it. Therefore, this is very simple. What is the name of this part? The name of this part is T of right. Therefore, T of right. We continue. Now, by this method, what will happen? It will establish a link like this. And now, this one is now broken. Now, this is broken. This is broken. And then the fifth one is now this is the one which is tricky. Now, what is the name of that node with R? There is no name. Now, how to access that fifth part? How to access that at left of R?
T of right of left.
Okay, that means fine, that's correct. Because R is having no name, therefore you directly cannot access. You have to access R using address which is saved somewhere. Now you know that once I have established this link, this address is also copied over here. Therefore, if I write new of right of left is nothing but 5, that's fifth part. Or it is also over there. Now, one thing, what is written by you, what you wrote over here. Okay, just let me see what you write. You wrote T of right of left. Now, T of right of left, is it true? Is it correct? It's wrong. T of right of left is now overwritten. Why? Because you already wrote 4. Therefore, actually, this is now no more there. This is not no more there. This is no more there.
New of right.
Because this is already overwritten by overwritten once you have modified 4. And therefore, this can only be accessed. This can only be accessed that new of right of left. Because new of right is 2400. 2400 of left is that fifth part. And therefore, this part has to be written like this. The fifth part I will write is new of right. New of right of left is equal to what you have to put? You put the address of correct. Good. You have to put. That means now you have established this name. Now this white link is now broken. Now this one is no more. This one is no more. Okay, now the white links are broken. And now you have inserted the node address position. That means you have to perform these five you have to perform this 5 steps. Okay. Now this is the whole concept. Here the chances of getting that link broken is not there. Therefore, in that case, you might be able to modify the sequence to some extent. I don't mean to say that you can very well modify. For example, you are going to modify both 4 and 5 together. In that case, you will lose things. Therefore, just taking the principle into concept that we have to modify the address of the new node first, you have to do like that. Okay. By this method, I can very well do this. Correct? That means with this insertion, you can do the other 2 insertions also. Insert at beginning, simpler. Insert at end is also similar, because what you have to do in insert at end, you have to only modify 3 pointers. Here you are modifying 4 pointers. Which are the 4 pointers? Here are the 4 pointers you are modifying. You are modifying this pointer 1, 2, 3, and 4. 4 pointers modifying. 1 is data, new of data. Therefore, you are modifying 4 pointers. But if you are inserting at end, you only have to modify 3 pointers. For example, I insert over here. You have to modify this 1, you have to modify this 2, you have to modify this 3. That's all. There are only 3 pointers. If you have to insert at beginning, again it is 3 pointers. For example, I want to insert here. You have to modify here 1, 2, and say this one 3. Only 3 pointers. But in the middle, you have to modify You'll have to modify 4 pointers. Okay, fine. Now I think it's clear to all of you that you can write an algorithm to delete a inside a node, add beginning, add end, in the middle I have laid it done. Now, in that case, the concept is same. It is much easier to do inside at beginning because there is no traversal. It is similar to the at end. You have to traverse from one to last. Therefore, obviously, this traversal has to be modified so that you will be able to do it till the end. Therefore, just write while t of data is while t of right is not equal to null, t is equal to t of right is going to come to this. And by this method, you can very easily try to do all the insertions. Now, with this one, what I will be doing, I will be doing. Any questions?
Sir, in insertion, like we are inserting at the middle or at the any point, we assume that we have already created the linked list. No, we have already some nodes in linked list.
It means that they already created a linked list is there. That means by successive insertions, the linked list will be something like this. Containing say 3 nodes, 4 nodes, 10 nodes, 100 nodes, anything, but the linked list already exists. Otherwise, if you want to create from beginning, you must create a no linked list, then insert that end, then insert that end or insert that beginning. And after say 5, 6 times, after 5 times, this will be like this. All those white nodes are after 5 times. It could be successive insertion deletions, successive insertions at the start or end, this will become like something like that.
So that means that if we are asked to write the algorithm for insertion a node at the nth position or at the beginning, then we do not need to check the whether the start has null or not.
No, in that case, if it is already there, but if you are doing it programmatically, you have to do that. If you are doing an algorithm, it means that the start is already there. But if you are writing a program, you have to do like that. Okay, so this is the way how you are going to do. Now, let us try to see what is the actual implementation. Now, if you just remember, I have done like this. I have done a tree like this. If you remember in the very early class, I wrote a tree something like this, maybe like this. Now, this is nothing but a tree, which is nothing but a hierarchical structure. The root node, the left child, the right child, and so on. Now, this is a binary tree. Why we call binary? Because it can have maximum of 2 children. Not necessarily 2, but maximum 2. It can have 0 child, it could have 1 child, or it can have maximum two children. Okay. Now this problem can be solved either using an array, which is not a good method, or using a linked list. If I am going to do a linked list, it is something. This nodes will basically convert like this. Convert like this. Okay, and these ones, these white lines, these white lines, they will change like this. Now, what you find over here, that this is nothing but the same as a double linked list. Now, here we will have a start. Now, the address of this node, maybe this address is suppose 2200 is stored over here. Because this address is 2140 is stored over here. Address of suppose 2600 is stored over here. Suppose address is suppose 2210. Now it is suppose 2600. Suppose 2800 is stored over. Now this is nothing but a double linked list. Okay. Now you might think of like this, but you can rearrange it as a double linked list. It is nothing but a. Now you can rearrange it. If you rearrange something like this, yes, I will try to show you. The left to start is this. Okay. Now left of this is 2600. Now left of right of 2210 is okay. Right of 2200 is this one. Therefore, in that case, you can try to do like you can convert it like this. Now, when you are going to, because each one is having either a left or a right. Now, by this method, you can very well try to make a double linked list. Now, this one can be, this is the one why you are doing, because the tree is boundary, in the tree is boundary, all the problem will be solved using a linked list one. Double link. Therefore, this finds a lot of importance in the case of trees, and all the problem of trees will be done using this concept. Okay. Now, just I'll stop at this moment, and then we'll do tomorrow the double linked list, and with some problems, maybe in this week I'll finish it the chapter, and we'll be able to do a lot of problems over there. Now, tomorrow, let's try to solve some of the questions. There are 3 questions which have been given to you. One, a question where I had given find multiple solutions for intersecting nodes. Today I gave finding a loop in a single linked list, how to find a loop, and thirdly, how to find. Now, one more question: how to insert the node at the start of the linked list. Now, with these 3 things, you can very well be able to clear, because there are a lot of questions which are there, which has to be done by you, and these questions are tricky. Therefore, in that case, the only thing what you can do is that how much you practice will ultimately be able to solve the things. Otherwise, that is the only way out. Otherwise, anytime you keep on asking, there are some questions which are always there, which are different from another.